Thank you very much. So I had some debt. There's stuff that I owe you from last time. It's behind the. I've recorded my debt behind the in the blackboard that you can't see. So maybe we'll get there today. I hope so. So, but before I go into that, I want to discuss a very important topic, which is behind the results that I still owe you, but it's also behind many, many other results. And this is the issue of divergence, or more precisely, non-divergence of Horocycle flows. So let me write quantitative non-divergence of Horocycle orbits. So the basic result here is you cannot have a surface such that when you apply the Horocycle dynamics to it, it goes off to infinity. Goes off to infinity means it has no convergent subsequence. It eventually leaves every compact subset of the space. So there's a theorem that says that for all m for any m is a translation. I'll remind you of our notation as I go along. So U sub s is our Horocycle flow. M is any translation surface in any stratum. And what I'm telling you is that when you apply the Horocycle flow to the translation surface, it cannot have this property that it eventually leaves every compact set of the stratum. Okay? And the idea behind this is what I call nondivergence of Horocycle orbits, and then there are strengthenings which I will describe. But let's think about this statement for a few seconds. First of all, you might also want to think about the geodesic flow. Convince yourself that the geodesic flow, this is absolutely false. Why is this false for the geodesic flow? Well, imagine your surface has a vertical saddle connection. So there's a vertical segment joining two singular points on your surface. And suppose you apply these matrices, the geodesic flow. So how do these matrices act on vertical segments? They contract them to zero. So as you apply the geodesic flow, this one saddle connection is getting shorter and shorter. And on strata, the compactness criterion is that you go off to infinity exactly if you have short saddle connections. And so it's clear that for the geodesic flow, you can construct divergent trajectories by choosing surfaces that have vertical saddle connections. And in fact, there are more complicated ways of constructing divergent trajectories, as most of you know. In order to rule that kind of thing out for the Horocycle flow, let's first understand what the Horocycle flow is doing to one saddle connection. We had this picture yesterday. It's a very simple picture. So let's talk about a length function. So gamma be a saddle connection on M. And let's define a length function. It's the length of gamma at time s. This is a function of s. So maybe I should. Gamma is a saddle connection M. I apply the Horocycle flow, I get a new surface U sub s of M, and on the same new surface, gamma is still a saddle connection, but its geometry has changed. It's just changed by the way that this is the origin, and this was our original holonomy of gamma. In other words, gamma was connecting two singular points by moving in this direction. When we apply the Horocycle flow, the holonomial is just going to move along vertical lines. So what this is for this function, so this is the picture in the plane, and what we're interested in is the length of these vectors, how the length of these vectors are changing over time. So as you can see, they're kind of linearly increase, and around this little square around here, that's essentially a constant function. If we use the soup norm on the plane to measure this length, we get a very nice picture. This is the s direction, and the function just looks like a piecewise linear function that goes down and then goes up again. Okay? And what I want to, so this is the graph of this function. And what I want to emphasize here is that if this is the if this is the y-axis and I mark 2 points, epsilon 1 over epsilon 2, from this geometry I can compare the amount of time in S where this function is smaller than epsilon 1, and I can compare it to the amount of time the function is less than epsilon 2. So the red interval is when the function is less than epsilon 2. The green interval is when this function is less than epsilon 1. Their relative size is essentially the relative size of epsilon 1 and epsilon 2. Yeah.
What is this constant interval?
So geometrically, it's you push the interval. Its norm is its horizontal segment for most of the time. The x coordinate is bigger than the y coordinate for most of the time. Then when you get close to the origin, suddenly it's the y coordinate that's bigger, and that's giving you the norm of the vector. So here you're decreasing x, but it's still more than y. This is just the height. This height here is just the height of the vector as it moves in the plane. It's moving along a straight line in the plane.
So you're measuring just the lengths of the silicon, Euclidean lengths of the silicon.
So I said maybe it's easier to use the soup norm just to see this precise picture. Measure lengths in the plane using the soup norm, and you see precisely this picture.
Oh, I see.
The soup norm is also called the L-infinity norm.
The soup norm is called the L-infinity norm. Thank you for the comment. Yes. Okay, so
I have a quick question about the statement of the theorem.
yeah,
Isn't the Horocycle flow ergodic?
right. The Horocycle flow is ergodic, so almost every orbit is dense, which means almost every orbit does go off to infinity along subsequences and goes to other places along subsequences. In fact, it goes everywhere. This is saying that there are no orbits that leave every compact set never to return. Going to infinity means you leave every compact set. Yeah.
I'm relaying your question here. Could you draw like a separate diagram where you show the orbit and relate the orbit to the graph?
So this point is maybe this point, and there's a little square area here where soup norm is equal to the height, and that's exactly this region here.
So the unit ball for the soup norm would be a square, right?
Yeah, that's this square right here.
That's a square, okay.
Yeah,
Sorry, so the graph is the soup of the heights?
yeah, it's a soup norm. Soup of the entries. You have a vector. The soup norm of a vector in dimension 2, I'm sure most of you already know this. You have a vector in dimension 2. Its soup norm is the max of its absolute values of its coefficients.
You're looking at the components.
Yeah, coefficients, components, yes. More questions about this? This was supposed to be a simple point. Yeah. No, gamma is some saddle connection, not necessarily vertical. And then I track it as I apply the Horocycle flow, and this is what it's doing in the plane. If I think about its holonomy, it's shearing this way. And then I think about its length as a function of time. And the length as a function of time does something like that. Okay?
So that point you've drawn is u sub s of gamma, is the coordinate of u sub s of gamma for some value of s.
Pardon?
You drew,
Well, I think
on your right-hand diagram, you drew a dot. That's
this is the origin in the plane.
s, and then there's a dot on your line.
This. This is like the starting point.
That's, yeah, so that's the coordinate of u.
This is the holonomy of gamma. This is the holonomy of gamma on M.
U sub s of gamma, right?
Well, this is, say, the initial point, for example, M.
Okay, then the other points would be.
And this would be the holonomy at us of M of the same gamma. Okay? For some value of s. And as I move, this is what I mean. Okay, those of you who don't believe me, I ask you to accept this on faith. So this is what's going on. So we're getting these functions, one for each saddle connection. And again, I want to emphasize the crucial property. Yes?
Why do you use the soup norm instead of the normal opinion norm?
Because all norms are equivalent, and the things that I'm going to be interested in are insensitive to these constants. And this is just the easiest picture to see from this geometry. So what I'm trying to stress, now that I think we all understand the picture, what I'm trying to stress is this feature that if you are short, suppose epsilon 1 you think of as epsilon 1 as being small and epsilon 2 as being moderate. So what this picture tells you is that if you're small for a while, then you're actually moderate for a while. In other words, I want to contrast this type of behavior with another function, potentially, which might have this kind of a behavior. It sort of drops down very rapidly and then goes back up again. Okay? And if you don't have this blue line behavior for horocycles, if you did have this blue line behavior for some map, and in fact this is what happens for the geodesic flow, if you did have it, what you'd be seeing is that the amount of time that this particular saddle connection is shorter than epsilon is almost identical to the amount of time that it's shorter than epsilon 2. So the amount of time that it's short and the amount of time that it's moderate are almost identical for this blue line, but for this white line, if you're small for a while, you have to be moderate for a pretty long time. Okay? All right. Now let's continue. And let's add to this diagram all possible lengths functions for all possible saddle connections on our surface. So our surface has countably many saddle connections, and we can just add countably many graphs to this picture. So here's another one. Here's another one. They all kind of look like that, except their slopes are different. Their slopes depend on the initial height of the vector. Now, what would be the picture if this theorem was not true? The picture would be that eventually, leaving compact S never to return means that for every epsilon, from some time on, there is a saddle connection of length less than epsilon. Right? So that means that, suppose that epsilon is what I drew as epsilon 1. So that means as I move off to the right, there's an entire ray, and that entire ray is covered by little pieces where at least one of these graphs is smaller than epsilon. So maybe I have more and more of these guys. And together all these intervals are covering my real axis. Is that clear? Why does that not happen? Let's think of let's first think of what's happening on the torus torus with one marked point, our favorite example. On the torus with one marked point, if you have two saddle connections, they are, and they're not saddle connections, they generate up in the plane a parallelogram. And the area of that parallelogram is at least 1. In other words, the shortest these two saddle connections are going to generate homology, and they're going to be giving you a little rectangle in the plane of area 1. So they can't both be short at the same time. So what that means is there's a little buffer here. So this picture is incorrect. And the reason it's incorrect is whenever so let me draw a more correct picture. Maybe I'll draw it over here. Whenever one saddle connection is in a certain region, maybe I'll draw that region higher. There's a certain threshold so that in this entire time period, when this saddle connection gamma 1 is moderate size, there's no other saddle connection allowed to be moderate size. Moderate size for me is length 1/2. On the torus, I can't have two different saddle connections, each of length less than 1/2. So there's no other, this is not allowed. You can't intrude, you can't have another line go into this picture and in this way. It has to wait until this guy has left before it can go in. Is that clear?
Can you say again why this is the case?
You have a torus. On the torus, you have a saddle connection. Saddle connections on the torus just correspond to loops going around the torus, because it's a torus with one marked point. So the parallelogram that they subtend has to, at least in terms of the area, the minimal area that it could subtend is the area of the surface, which is 1.
Are you still only talking about torus? Not
For the moment, I'm explaining the proof for the simple case of a torus with one marked point. Yeah.
For more coordinates for your graph, so the line you've drawn is the line at height 1/2.
Yeah, this is height 1/2. Yes. Yes.
So why can't your cost be big? Why can't you take an epsilon or like equal to 1? Can't use that area.
I'm claiming that the orbit doesn't escape to infinity. To say that it doesn't escape to infinity means that it enters into every cusp eventually, and I take the cusp corresponding to this value. Okay? So this means that every time you go into the cusp, you have to go back out, and in fact you have to spend a long time in a kind of an intermediate region. The times when your length is in this interval is much larger than the time when your lengths are in this interval. It doesn't matter what the slopes are, about the relative amount of time you spend with saddle connections of moderate size, where now I'm taking moderate to mean between 1/2 and epsilon, is much larger than the amount of time in which you have small saddle connections, which I take to mean saddle connections of length less than epsilon. In fact, the ratio of times is essentially epsilon. Okay, that comes exactly from this length comparison. Okay? Okay, this was the crucial, so there are two crucial points here. The first crucial point was just the behavior of these graphs. It's kind of very, very slow and regular. The second crucial point is where I use the geometry of the torus. You can't have two simultaneously short saddle connections. The second point becomes much more complicated for higher genus surfaces, for other strata, and it's no longer true, and there's a replacement. And the replacement is an idea that's called combining complexes or separating curves, which appeared in a paper of Kirchhoff, Mazur, and Smiley. And basically kind of philosophically, what one can say, and I'm not going to go in, it's a difficult combinatorial argument. What I can say is, if you might have two short saddle connections on the surface at the same time, okay? But typically what happens is that short saddle connections cluster in little subsurfaces, and those subsurfaces have some topology. You cannot have a short saddle connection which is on the boundary of a cluster intersecting another short saddle connection which comes from which hits another sector, another cluster. Okay, I don't want to go too deeply into it, but just imagine that your surface has little subsurfaces where there's lots of saddle connections. Then this is false. You can have lots of simultaneously short saddle connections, but they cluster in some way and they form little subsurfaces with boundary called complexes. And to understand this type of phenomenon, you need to understand how those complexes interact. And so you get this kind of a buffering idea. Okay, that was supposed to be a kind of a rough sketch of how one proves this result. But what you could see from this rough sketch was that it was proving more. I wasn't just proving that the Horocycle flow doesn't go off to infinity. I was actually proving that if I take a compact set large enough, well, in other words, if I take this parameter epsilon 1 small enough, the amount of time in which the surface is outside of this compact set becomes smaller and smaller. So asymptotically, your orbits are spending all their time, except for some very small proportion, in a large compact set. So there are various strengths of this basic theorem, and I want to write one of them down, and one of them I'll also later use one without writing it down. So let me write down a strengthening. So it says the following. So for any, there exists a compact subset of your stratum such that for any surface in H, one of the following hold. The first option is that the surface has a horizontal connection. If a surface has a horizontal saddle connection, then in terms of these graphs, I should allow that. Horizontal saddle connections, their length doesn't change. They're just stabilized by the flow. So the graphs I'm getting are just constant graphs. That could also be the case. So that's a case I have to take into account. If that doesn't happen, all these graphs are actually going up and down, and I can tap into the argument, and I can then prove that the lim inf as t goes to infinity of the relative amount of time on an interval of length t in which my orbit is in this compact set is at least a half. Okay, so take a look at the second statement. It's saying that asymptotically my trajectory spends at least half of its time in a fixed compact set. And this fixed compact set is completely uniform on the entire stratum except for one possible counterexample, which would come from having horizontal saddle connections. This is the strengthening that I will use when I discuss Smiley's theorem. So let's turn to that. So let me pull up so you can see what I owe you. When you get your bank statements, it's always useful to take a good look. So just make sure that I didn't, that I'm going to keep the promises that I made yesterday. Didn't reduce the number of promises. So yesterday I said I would prove two things today, at least. One of them is Smiley's theorem, which says that if you have a closed orbit for the SL2R action, then the surface is in fact a lattice. Okay? And the second statement is, okay, so we'll get to the second statement later. So let's sketch the proof of Smiley's theorem using this divergence result. So what do I know? I know that the orbit of M is its translation surface. I know that its orbit is closed. And as we saw yesterday, that the orbit is closed, which is the same as saying that the orbit map, which is this map, is a proper map. In other words, the homeomorphism. Onto its image, which is the orbit. Gamma here is the Veitch group. And what am I trying to prove? I'm trying to prove that the Veitch group is a lattice. So a priori, this gamma might be empty. Might be the trivial group. In that case, maybe this is what I want to fight. Maybe there's a kind of a nicely embedded, closed SL2R orbit, which has no stabilizer at all in the moduli space. I don't want to rule that out. OK? Well, if this is true, I can take the Haar measure on G mod gamma. That gives me a nice locally finite measure on G mod gamma. I can push it under this homeomorphism, and I get a G invariant locally finite measure on the stratum. So push Haar measure using this map, get a locally finite measure mu on the stratum, which is G invariant. And so what I'm going to show you is that any such locally finite measure has to be finite. If it's finite, that means it was finite over here. That means this quotient had finite volume. So we need to show that mu. Locally finite now means that it's finite on compact sets. Okay? So there's a theorem in ergodic theory which is called the Hopf ratio ergodic theorem. Let me write down Hopf ratio ergodic theorem. I'll just write it down for our setup. So the Hopf ratio ergodic theorem says the following thing. If you take any two functions, which are L1 functions on our stratum, and here mu is allowed to be infinite. Mu is some locally finite measure, or in the general formulation, it's a sigma finite measure on a measure space. So in particular, it works for our mu. Any two functions, let's assume that that f2 is non-negative and has positive integral, and you look at the following ratio, then for almost and also for any f1 and 2, if mu is U ergodic, then for almost every M, here's what I have. So I integrate F1 integrate f2 along the orbit for times between 0 and t. So I get longer and longer sequences of time starting at this point m. I integrate my two functions, then I take the ratio, and then I let t go to infinity. That should converge, and it should converge to the ratio of the integrals. Okay? Yeah.
You said the integral of f2 should be finite, not positive, right?
Pardon? Sorry. Both of the integrals should be finite because we're in L1, and the integral of f2 should be, well, I guess non-zero is what I want. I mean, I just don't want, I want this to be well defined. Yeah. This is a general theorem for flows. Flows on sigma compact measure spaces. Okay, now most of you know the Birkhoff-ergodic theorem. This is a variant of the Birkhoff-ergodic theorem that also works for infinite measure. Just think of what would happen here if our system had finite measure, and let's give an example, e.g. mu finite f2 is the identity function 1. If f2 is the identity function 1, it belongs to L1 because the measure, if we assume the measure to be finite. And then the bottom is t, so this is the integral divided by t, and this becomes the space integral normalized. And so that's exactly the Birkhoff-ergodic theorem. Okay, so this gives you the Birkhoff-ergodic theorem. So it's a strengthening of the Birkhoff-ergodic theorem to infinite measure systems. Okay, let's apply this. So take K compact as in the strengthening. That I have up here. And K1, another set. And let's let F1 be the indicator of K1 and F2 be the indicator of K2. And let's see what this theorem says. So let me rewrite the bottom. So the top is, if you're integrating an indicator, you're just measuring the amount of time you're in your set. So this is the times between 0 and t for which your orbit is K1.
So which of K1 and K2 is K?
I'm sorry. K2 is K. Okay, this is what we're integrating. Okay? And by the Hopf theorem, this tends to the measure of K1 divided by the measure of K. And on the other hand, I want to bound this from above. So this is obviously bounded by T. The top is obviously bounded by T because it's a subset of the interval of length T. And the bottom is bounded below by half T for large T because of this strengthening. So this is and here we used Hopf. Okay, the t's cancel out and we're left with a 2. So we're getting that mu of K1 is less than or equal to mu of K, 2 times mu of K. And now we take a soup over all the K1, and you get that the total measure, mu of the entire space, is less than 2 times mu of k, which is some finite number. So I've proved to you that using the strengthening that the measure is finite. Okay? And did anybody detect when I was fooling them? What? Ergodicity, yeah. So I cheated once only. I claim I only cheated once. I'm assuming that U is ergodic here. And it's not given to me that U is ergodic. All I know is that the measure comes from a G ergodic system because it was a push forward of a space on which G acted transitively. So there's a ergodic decomposition result that one can use here that allows me to assume that, that mu is ergodic. Any questions about this proof of Smiley's theorem? Yeah.
Sorry, I didn't understand why the denominator was bigger than
This? Because of this. That's exactly what that says. I mean, in the limit. Okay. Right. Thank you. I forgot to say that. So that's an important point. So the measure that we had was a G invariant measure. So it's invariant under rotations. So almost every surface has no saddle connections. Almost every surface with respect to this measure has no horizontal saddle connections because I'm allowed to rotate surfaces, and therefore I can assume this. You're right. Okay. I'm going to lower the board, I guess. And now my goal is to prove the proof of the second statement here, which was left over, which is that any surface, if I take its orbit closure under the Horocycle flow, I can construct a completely periodic surface in the closure. And here I'm going to be slightly more vague regarding how exactly the nondivergence gets used, but it gets used exactly at the crucial technical point. Let me remind you of a notation that I had yesterday. The notation was this notation capital Xi. Capital Xi of a surface M is the graph of horizontal saddle connections on M. And so the proof, so what am I proving? I want to prove that any orbit under the orbit of any surface under the Horocycle flow contains a completely periodic surface in the horizontal direction. So let's understand what completely periodic means in the language of this Xi thing. So when you're completely periodic, all your singular points are on boundaries of cylinders, and every horizontal ray issuing from a singular point actually lies along the boundary of the cylinder, so it's actually a horizontal saddle connection. So when you're horizontally periodic, you have the maximal possible number of horizontal saddle connections, and that's in fact a characterization of being horizontally periodic. Okay, is the geometry clear? So we have topologically surface singular points, which I can think of topologically as these kind of vertices of some graph. And these things poking out are the horizontal directions at those singular points. And for some of these, there might be a horizontal saddle connection going out and in, and maybe there are more. You know, this could be the picture for your C. And then if you're horizontally periodic, all of these prongs actually become part of Xi. And if you're not horizontally periodic, then starting at the prong that's not part of a saddle connection, you get some kind of infinite line in your surface. Of course, it doesn't cross the saddle connections, it's horizontal. Infinite line in your surface, that's sort of infinite horizontal ray on your surface that's accumulating somewhere, and that's all you know about it. Okay? And I'm trying to show you that I can always make this Xi maximal, and so to make all the prongs occupied. So the goal, find M prime in the orbit closure of M so that C of M prime is maximal, where maximal means there are none of these red lines. All the prongs, all the separatrices starting at all singular points are actually on saddle connections. And to do that, I'm going to work by induction. I'm going to start with M and pass to the closure under the Horocycle flow in such a way that I've picked up a new saddle connection. So recall from yesterday that as soon as I have horizontal saddle connections on a surface, when I apply the Horocycle flow, they're not going to move. They're still there. Horizontal saddle connections don't change under the Horocycle flow. So Xi, recall that Horocycle flow preserves horizontal saddle connections i.e. for any surface, if I apply the Horocycle flow, I'm not changing the saddle connections that I already have. But I may pick up more in the limit, and that's what I want to do. So let's start with an M. So strategy, find M prime in the orbit closure of M such that the cardinality of this object on M prime is bigger than the cardinality of this object on M, unless so. And continue by induction. When I say continue by induction, I'm using the fact that if M prime belongs to the orbit, just one second. I'm using the fact that if M prime belongs to the orbit closure of M, and M double prime belongs to the orbit closure of M prime, then M double prime in fact belongs to the orbit closure of M. This enables me to keep going in the induction. Yes?
I'm letting, so X is probably psi.
Where did I write X?
Don't find M prime. X, I mean, it's
Yeah.
there is something.
Yeah, you're absolutely right.
So all have to end somewhere. This red
Yeah, this red stuff doesn't exist. Okay, so what happens if the red stuff does exist? So I have a horizontal infinite ray on my surface, and let's draw it kind of in a more realistic manner in terms of the flat picture. So here's the singular point, and it has its cone angles, and the foliation does something like this. And this is an infinite ray issuing. This entire picture is embedded in my surface, and this is the infinite ray that's drawn in red on the left-hand side. It's an infinite object. So these infinite rays, if they don't close up, they accumulate on something, and that something is actually a subsurface, and that subsurface actually contains singular points. So what that means is that as you're traveling along this ray, you have to be coming closer and closer to singular points. So in other words, I can draw a picture of singular points that get seen as I move along this ray. Of course, there might be repetition. I'm probably seeing the singular point over and over again, but I'm seeing it with a different holonomy. In other words, let's denote the holonomy of this vector by x1, y1, and so on. So we get this sequence xi, yi, where the xi's are going to infinity, and the yi's, let me put absolute values, the yi's are going to 0, but the yi's are actually not 0, which is important. Okay? I put absolute values because I don't know whether these guys are under the x-axis, and I don't know whether the prong is going to the left or to the right. Okay, now let's use a Horocycle flow, and I'm going to use the Horocycle flow to move. So take for each I, define a SI by the following geometric requirement. The vector, image of the vector xi, yi under the Horocycle at time si, I want that to have the x coordinate equal to 1. So this is 1. I set this to be 1, and this to be yi. Okay, so on the other hand, I know exactly what this is. This is xi plus s yi. So si. So this is the equation that I need to solve in order to find this yi, in order to find this si. Okay? Where does what live? This is kind of a picture that's embedded in my surface M. Okay? I haven't shown you the entire surface. What I've shown you is I took one singular point. It's the singular point that this red line starts at. And I'm pushing that ray into the surface. And around it, I'm drawing a little flat chart. So you should think as some neighborhood of this infinite ray embedded in my surface. And because of general facts about these flows, it has to come either close up, be inside a cylinder and close up, be the boundary of a cylinder and close up, or it has to come close to singular points. So what I'm doing is I'm taking each one of these and I'm kind of moving it back. You know that the Horocycle flow moves points horizontally in horizontal lines. I'm moving it back. If yi is small, this is going to take lots and lots and lots of time, but y is non-zero. So eventually, I just wait, and it has length 1, and then I stop, and that's the definition of SI. Okay? What did I get? I got this surface, let's denote it by MI. So on the surface MI, which is USIM, there is a saddle connection with holonomy one yi. One yi tends as I tends to infinity to 1, 0. Let's assume that these mi's converge to some surface. The mi's are some surfaces somewhere in the stratum. Let's take a subsequence where they converge. So suppose the mi converge maybe along a subsequence to M prime. Pardon?
Why is it the case that subsequent?
I said suppose.
Okay.
It's true because I said you should suppose it, so you should please suppose it, Vincent, for the moment.
Produce a new set of connection, but have some possibility that some original set of connection eliminate.
I couldn't hear you.
In this case, you just produce new set of connection.
Right.
But you should argue that no original set of connection should be eliminated.
Thank you very much. No saddle connection is eliminated because of this. So all of the surfaces Mi have all the saddle connections that M had. They're just there forever. They can't change. And in this way, we're producing a new saddle connection. So M prime, the set of saddle connections of M prime, properly contains the set of saddle connections of M. Okay, this is kind of a, there's some topology hiding here in the background. So, but okay, let me just this is supposed to be a sketch of a proof, not a proof. So you have this containment. One should sort of think about how to make sense of it. But I'm claiming at the very least that the number of saddle connections has gone up because along this subsequence, I always had the same number of saddle connections, and in the limit, I got one more. And now I want to address Vincent's question, which is, of course, a good question. So Vincent is kind of an unorthodox person, and you tell him to suppose something, he says, well, what if I don't want to suppose it? So he doesn't want to suppose it. So how do you fix it? So so this is the main issue, in fact. Main issue. What if the MIs don't converge? What if they go off to infinity?
Sorry.
Yeah.
I'm still actually stuck on the question I was asking for.
Right.
So what if like the other saddle connections are becoming shorter and shorter as you apply these?
The horizontal saddle connections are not becoming shorter and shorter because their length is fixed. Horocycle flow doesn't affect the lengths of anything that's already horizontal.
But how do you know you get a new saddle connection that does not coincide with solid infinity?
So what could happen, there are various, that's why I said that there's some topology. There are various topological cases. One thing, I could take this number 1, for example, to be shorter than all the saddle connections that I already had. Change the proof a little bit. I could analyze the various cases, and in some of the cases what might happen is that I had an old saddle connection that looks like this, and suddenly I pick up a new saddle connection right here. So there's some topology to worry about, but in any case I'm claiming that the number of saddle connections increases. The way to see that is just think at the singular points, just think of the number of prongs that are occupied by horizontal saddle connections. And you just see that I have to increase the number. Yeah?
So what happens if you just take 0 instead of 1?
That's not a stupid curiosity. That's a curiosity that I want to return to in a second. Okay?
So
Yeah?
in the statement that's written there, on MI there is a saddle connection. It's not horizontal. Is that correct?
No, it's not horizontal. It's almost horizontal. It has this holonomy. Its horizontal component is 1, and its vertical component is close to 1, but close to 0, but not 0.
And where did you get it from?
That's this one. It was on M, and it was pushed until it had exactly this holonomy, and that was the definition of MI.
But I thought it was just another singular point. Why was there?
So there's a line. I connect these 2 points by a line. That's a saddle connection, and then I move the surface so that this saddle connection has this holonomy. Pardon? So there
You're
you
not allowed to just draw a line.
right. Absolutely. So to be more precise, when I embed this line, I want to think of it as kind of embedded in a particular way that allows me to, in fact, insert these lines. And this can be done. Does that answer your question?
No.
You have okay, yeah.
The graph itself it's an infinite graph. Yeah?
The graph itself, it can have, is the number of edges is bounded once and for all by the total cone angle of the surface. You have finitely many singular points, finitely many horizontal lines coming out of each singular point. So the number of edges is bounded once and for all.
No, but you can write it in many ways.
So the red lines could be infinite. This is a graph. It's got two kinds of edges. One kind is a standard edge going from vertex to vertex, and another edge is not an edge of a graph. It's an infinite ray that starts at the vertex and shoots off to infinity. But there are only finitely many of all these things. Yeah.
So what happens is below the singularity, there is another singularity on the horizontal edge.
Let me not, I'm giving an indication. I want to move on. This is a topological issue. You're right to raise it. It's related to the previous question, which probably I didn't explain very well. I can answer when we're done, which is coming up. So let me conclude with the two questions that were asked, which were very good questions. Why can we assume that the MIs don't go off to infinity? And what happens? We set this, there was this weird number that maybe you've heard of before, which is 1, which I chose in the proof. I just set this to be 1. But as Giovanni is saying, I can set this to be 0. Nothing's preventing me from setting this number to be 0 or any other number. And I want to address those two questions. So first of all, why doesn't the thing shoot off to infinity? The answers to both questions are actually related. So the answer about why this thing goes off to infinity, well, it could go off to infinity, but instead, and then what I do is, instead of making this number actually equal to 1, I make this number, I look at the interval of s's, where this number is between, say, 1 and 2, okay, or between any, 1.1 and 1.2, or whatever I want, some definite interval on the real line, okay? So what are these times? What's this sequence of times? The sequence of times is a condition on S, which gives me an interval. And because the motion is smaller and smaller, these intervals are actually getting longer and longer in Horocycle time. And then there's a strengthening of the nondivergence for unipotent flows that says on these long, long intervals, you must be able to find a subsequence that converges in your stratum. So let me just write that down. So fix, define Si as above, Si prime, so that the US Si prime of xi, yi. I define it with in the same way, except I replace 1 by 2. And for S between, and look at the interval of times between Si and Si prime gets longer and longer. By nondivergence, which is by a strong form of nondivergence, which I haven't stated, I can choose Si double prime in this interval so that these surfaces do not diverge. Okay?
But it gets longer, you mean as I goes to infinity.
As I goes to infinity, this is a longer and longer interval. It's basically 1 divided by yi. To answer Giovanni's question, this argument, if I set this 1 equal to 0, in fact, then this just means that this Horocycle orbit has to come closer and closer to the cusp, and which means that, proves another statement, that in fact, if my orbit was not originally horizontally periodic, then its orbit is unbounded in the stratum, which is also interesting. So I'm completely out of time, is that right?
No, you are just in time.
Oh, so I'm out of time, but not completely out of time. Yeah, so I was planning to do much more, but I guess At least I paid my debts, I think. And you'll hear more from John tomorrow. Thank you very much.